Well, welcome everybody. It's good to see you all. I recognize some faces from recent other library programs, so thanks for coming back again to Zoom. My name is Malia Sanford, and I am the programs manager at the Lopez Island Library. And I'm so pleased to welcome you and thank you for coming to this evening's program, featuring author Tor Hansen, who is here to speak about his newest book, Hurricane Lizards and Plastic Squid, The Fraught and Fascinating Biology of Climate Change, which explores the remarkable ways that plants and animals are responding to climate change, moving, adapting, and even evolving. This program is part of our fall series of local author talks, and we are cheating just a tiny bit because Torres lives on San Juan Island, but we are staying within the county, so hopefully that counts. After tonight's program, we have one more local author to finish up this fall series, and that is Peter Kavanagh on December 7th. He will be sharing his newest collection of bird photography titled 100 Flying Birds. And he will also have an art show at the library in conjunction with his author talk that will be up December and January. So please save the date for that final program in the series and plan to come check out his photographs sometime when you're in the library. And you can register for that program now at lopezlibrary.org/local authors. And now I'm so pleased to welcome author and biologist Tor Hansen, who is a Guggenheim Fellow, a Switzer Environmental Fellow, and winner of the John Burroughs Medal. His books include Buzz, The Triumph of Seeds, Feathers, and The Impenetrable Forest, as well as the illustrated children's favorite, Bartholomew Quill. Tor's work has been translated into more than 10 languages and earned many accolades, including the Phi Beta Kappa Award in Science and 3 Pacific Northwest Book Awards. He co-hosted the PBS nature series American Spring Live and has been a guest on programs ranging from Fresh Air to Science Friday, On Point, and Book Lust with Nancy Pearl. Hurricane Lizards has been shortlisted for the Pacific Northwest Book Award. It is a New York Times Editor's Choice book, a Publisher's Weekly Pick of the Week, and a Powell's Pick of the Season. So congratulations, Tor, for all of that recognition on your newest book. And thank you so much for sharing it with the Lopez audience. After Tor's presentation, there will be time for audience Q&A, but please join me in welcoming virtually author Tor Hansen.
Well, thank you all very much for the lovely welcome, Malia, and the nice intro. It is a pleasure to be with you, so to speak, there on Lopez virtually. I'm sure we all wish we could be in the same room for these presentations, but that day will come again, I'm sure. And in the meanwhile, we can thank the Zoom gods for these virtual opportunities to get together. And with that in mind, I'm going to try a Zoom trick here and share a portion of my screen with you. Now, I hope that everyone sees a book cover. Nod your head if you see a book cover. Okay, we're in business. And I want to kick off right away this evening with an image that we are all extremely familiar with, the iconic picture now of a polar bear stranded on a melting iceberg. This has really become our go-to symbol for the biological impacts of climate change. So much so that, in my opinion at least, the conversation far too often stops there. In the media and in all kinds of public discourse, we invoke the poor polar bear as sort of a dire warning and then move on. And in doing so, ignoring this vital biological backstory to the climate change crisis. something that is really at the heart of any climate change scenario, because after all, what matters is not so much the change itself as the response to the change. If every species got along just as well in all conditions, then tweaking the weather a little bit wouldn't matter in the slightest. But of course, that's not how nature works. The diversity of life on this planet stems from specialization, a great accumulation of species that have adapted to particular environmental conditions. And when those conditions change, species react. And it is the sum of those reactions that will determine the future, theirs as well as our own. So this evening, I want to focus on the challenges that climate change creates for plants and animals, and how we can already see and measure in real time their responses playing out all around us. We won't be talking very much about the process of climate change, the atmospheric stuff, with one exception, and that is carbon dioxide. Has there ever been a substance so often invoked and so seldom explained? Before I began working on this book, I realized that I hardly knew anything about the stuff that was making the planet warm in the first place. Yes, I did remember the image from my high school chemistry textbook, the carbon dioxide bit there with the molecule with the atom in the middle, the carbon, the big black one, bookended, if you will, by these two red oxygen atoms. Maybe you have the same image in your textbook in high school. I do remember at the time thinking to myself, that looks just like the head of the red-eyed fruit flies that we just spent the whole last semester studying in biology. And that connection sort of stuck with me through the years, so that when CO2 became notorious for its connection to climate change, all I could picture was the smokestacks and tailpipes of the world emitting these clouds and clouds of tiny flies, which was a vivid image, but not particularly helpful in really explaining the situation. Because carbon dioxide is a bit of a paradox, isn't it? I mean, it's a global threat, but it's also one of the building blocks for life on Earth. It is everywhere in the atmosphere, which is why it was the first atmospheric gas ever to be described and named. Before scientists discovered carbon dioxide, they weren't even sure what the atmosphere was, or if it even contained anything that one could measure. Now, the discovery and much of the early work on carbon dioxide, the credit for that goes to this fellow here, a fellow named Joseph Priestley, who was an 18th century clergyman and chemist, an all-around polymath. He was good friends with Benjamin Franklin. He was just in the thick of the scientific community at that time. And Priestley, in turn, credits his work on carbon dioxide, all of the discoveries he made, to the happy circumstance of living right next door to a public brewery, where he found quantities of this gas, this colorless, odorless gas, collecting above the fermentation vats. And he also found brewers who were patient enough to let their local vicar build a scaffold over the top of the vats and then lower all manner of experiments into that invisible cloud. And he learned in doing so a lot about carbon dioxide. He learned that it would snuff out a candle flame, and he knew that it was heavy because he could see the smoke from the snuffed out candle flame going downward to the brewery floor in this invisible gas. He learned that when he lowered insects and small animals into it, they could not breathe. And he learned that he could dissolve this gas in water, and in doing so, produce a fizzy beverage that had what he called a pleasant, acidulous taste. Now that breakthrough earned him the prestigious Copley Medal from the Fellows of the Royal Society of London, but it earned quite a lot more for an entrepreneur named Johann Schwepp, who copied Priestley's methods to found the soda and tonic water company that still bears his name. So Priestley's work paved the way for all sorts of other experiments on carbon dioxide. Tindley here and others working on this gas and learning things about it, they soon realized that it would retain radiant heat. You could heat up this gas and it would retain it more than the air itself. And as early as the 1890s, scientists realized that industrial activities were adding enough of this stuff to the atmosphere to warm the planet. As early as the 1890s, this was discovered. Of course, that work was done in snowy Sweden, where the idea of warming up the atmosphere by a few degrees was generally greeted with gusto. They thought it was a great idea. So we have known then for a long time that carbon dioxide was a greenhouse gas. But that doesn't really explain why some of it is a threat and why some of it is benign. I wanted to get my head around that distinction. I really wanted to get my hands on some CO2. So I conducted a little experiment at home on the contents of our refrigerator. I got my young son, Noah, to help me in that endeavor. And this is the story of that, which comes straight out of the book. I'd like to do a short reading for you now from chapter 2 that begins with a quotation attributed to Galileo, who said, "We must measure all that is measurable and strive to make measurable all that is not." It turns out that fermentation occurs in a lot more places than vats of beer. Yogurt and cheese makers call it culturing, but it's more accurate to think of it as a form of slow microbial digestion, a way for bacteria and other tiny organisms to extract and use energy from the foods they live within and around. And like any form of digestion, it is a process that produces waste. Luckily for food lovers, the byproducts of fermentation include things like alcohol, thus the beer, and lactic acid, which adds tanginess and pungency to such cultured favorites as kimchi and buttermilk. Most fermentation also produces carbon dioxide, which is what had me combing through the back reaches of our refrigerator. A container of organic sauerkraut advertised probiotic punch and claimed it's alive. But any organisms that kraut might have once contained had long since shuffled off their mortal coils and were no longer producing a whiff of carbon dioxide. A lit match held above that briny mix burned brightly. Experiments with yogurt and sour cream were similarly disappointing, but then we hit the jackpot. On the bottom shelf, behind the bags of carrots and celery, sat a half-gallon jar of homemade pickles. They had been stewing in their own juices since August and tasted yeasty as well as sour, suggesting that fungi had joined the bacteria in their digestive pursuits. Frankly, it was past time to throw the pickles out. But for once, procrastinating a chore had paid off. As soon as Noah and I brought a match near that open lid, the flame demonstrated why carbon dioxide is such a common ingredient in fire extinguishers. With no oxygen to burn, the match went out in an instant, as if we'd turned off a switch. What's more, the smoke from the snuffed tip curled downward, trapped in the gas, just as Priestley had described. "It's pouring down the side," Noah exclaimed, watching as wisps of smoke followed the heavy vapors over the jar rim and down to spread across the countertop. "That's it," I told him. "You saw the carbon dioxide." He quickly brought me back to earth. "I didn't see the carbon dioxide, Papa. I saw the smoke." But like Priestley before us, we could use that smoke to watch the gas, defining its boundaries as it flowed and swirled around the open jar. For a few minutes, our kitchen was filled with the thrill of discovery as we lit match after match, watching them snuff and smolder until all the carbon dioxide had dissipated into the surrounding air. Simple experiments often lead to broader insights, and repeating Priestley's fermentation trick brought up an obvious question. Do pickles cause climate change? Does making beer? The answer, of course, is no. But understanding why some carbon emissions are harmless while others are not reveals a basic truth about climate change that we rarely stop to think about. In the case of our pickle jar, the carbon dioxide came from the cucumbers in the brine, and the cucumbers had gotten it from the air around our garden the previous summer. Like plants everywhere, their growth relied upon photosynthesis, that leafy process of combining CO2 and water with energy from the sun to create starches. In other words, carbon dioxide puts the carbo into carbohydrates. When those starches break down, the carbon dioxide goes back into the atmosphere. This is the step in the Earth's carbon cycle with which we are most familiar, because we play a role in it every moment of every day. Whether we eat plants or eat animals that have eaten plants, the energy that fuels our bodies traces right back to those photosynthetic starches, and we release carbon dioxide with every exhaled breath. But in terms of climate change, breathing is like making pickles or brewing beer, guilt-free. That's because our bodies are just one short stop for carbon on its continuous circuit from the air through plants and animals and back again, with no net gain or loss. If that's all there was to the story, then the planet wouldn't be warming and I wouldn't be writing this book. The reality of modern climate change hinges on one key fact. Not all plants break down. Consider the pickle. Cucumbers eaten fresh or left to rot in the garden compost release their carbon right away, but that process slows down considerably in a jar of salty brine. Under the right conditions, it can stop altogether. In nature, this occurs primarily in two locations, the ocean floor and boggy wetlands. When marine algae die en masse and sink to the seabed, they sometimes get buried before they are eaten or decomposed. Dead plants in bogs can also accumulate with little decay, forming layer upon layer of peat. In either case, if sedimentary rocks develop above and around these organic deposits, their carbon is effectively trapped, removed from the atmosphere for millions and millions of years. Transformed by heat, pressure, and age, we recognize these ancient plants as the fossil fuels. Petroleum from the algae, coal, which comes to us from the peat, and natural gas, which comes from either. Burning them now returns all of that stockpiled carbon dioxide to the air at once, overwhelming the natural cycle and leading to all of the many consequences now unfolding. So the next time you find something in the back of your refrigerator that looks like a scientific experiment, it is a scientific experiment. There's a lot to be learned there. And it's a good reminder for all of us that even the atmospheric aspects of modern climate change are rooted in biology. So we know that the climate is warming and we know why, but what does all of that mean for plants and for animals? As you can imagine, this is now a booming field of study. Climate impacts are so widespread in nature that it's not too much of an exaggeration to say that all biologists are studying climate change. Some of them just don't know it yet. And it helps to organize that deluge of information into themes. And one of the most common climate change biology themes has to do with timing. At Walden Pond, for example, the violets as pictured here, and also the wood sorrel and other plants that Henry David Thoreau admired in May and June now bloom by late April. And what he called that early yellow smell of willows can reliably be savored in the middle of March. Spring is arriving earlier and earlier. You can see it happen in your own backyard. And if you write your observations down, as Thoreau did, they might one day become valuable. His meticulous notes on the plants and the birds that he saw at Walden are now a vital baseline for modern comparisons. One expert told me that if Thoreau was listed as a co-author on all of the papers now using his data, he would be one of the most prolific climate change scientists of the 21st century. But a modern spring isn't just earlier than what Thoreau saw, it's different. To him, it might seem like a season in disarray. That's because not all species are responding in the same ways to climate change, or even at the same times. This flower, for example, is familiar in meadows throughout our San Juan Islands and throughout the American West. It is known as death camas. Like many plants, death camas produces toxins to ward off would-be attackers. But unlike most other plants, it doesn't just put those chemicals into its leaves and its seeds and the other places that are likely to be nibbled by an herbivore. It puts them everywhere, including into its pollen and its nectar. And what's more, the main toxin in that mix, zygosine, is especially nasty stuff. It attacks the heart, it attacks the lungs, and for good measure, it attacks the digestive tract. The Latin name of death camas really says it all. Toxicoscordion venenosum venenosum. Poisonous bulb, poisonous, poisonous. So death camas is very well protected. But in terms of pollination, that puts it in a bit of a bind. After all, how do you attract insects to your flowers when instead of a tasty reward, you are offering them seizures, paralysis, and, well, death? Enter the appropriately named death camas bee, one of only a handful of species and the only bee that has figured out a way to tolerate death camas poison. Now that gives the bee an exclusive source of pollen and nectar, and it gives the flower a very dedicated pollinator. It's a very tight, specialized, codependent, and co-evolved relationship. But in many locations, death camas now blooms weeks earlier than it did just 30 years ago, responding to the steady rise in springtime air temperatures. The bee, on the other hand, nests in the ground, where temperatures are warming more slowly, and it's still on the old schedule. And if that trend continues, it threatens to pull apart these co-evolved species, not in space, but in time, creating what biologists call a timing mismatch. The flowers too early for their bee, and the bee too late for their flowers. So specialized relationships like pollination are particularly vulnerable to timing problems. But mismatches have been cropping up all over the place. In the Arctic, for example, where caribou migrating toward their calving grounds in some cases now are arriving past the peak of plant productivity in those landscapes. The plants, of course, that they were counting on to raise and feed their young. Similarly, the migration of shorebirds, flocks now arriving in some cases at mudflats past the peak of productivity of the invertebrates, the worms and other creatures in those mudflats that they were relying upon to fuel the next stage of their journey. Now, it can take years or decades of work to really understand and figure out the long-term consequences of some of these mismatches. They play out in many cases over long stretches of time. There are other climate change challenges that are much more immediate. Extremes, for example, in terms of increasingly harsh climatic conditions, the extremes in storms and floods and droughts that are pushing species beyond their comfort zones. We're very familiar with this in the San Juan Islands just from the last few months, even the last few days, as we have seen extremes in heat from the heat dome this summer, extremes in rainfall from the records being broken just a few days ago. As one expert told me, we'd been talking about timing mismatches and all these complexities, and he said, but remember, you know, sometimes it's pretty simple. Sometimes creatures just get too hot. And one such example comes to us from the deserts of the American Southwest, where you might expect that creatures would be well prepared for a warmer world. They live in the desert, after all. This is a story from Barry Sinervo, who is a herpetologist at the University of California, Santa Cruz. And Barry studies lizards, including this creature here, the western fence lizard. A species which, if your childhood was anything like mine, you may have tried and failed to catch, because the lizards would always scurry away at the last moment to hide beneath a rock. Well, it turns out that fence lizards use rocks for a lot more than escaping young lizard enthusiasts. They are what biologists call heliotherms. They use the sun, the helio, to thermoregulate their body temperature. They bask on the tops of rocks when they need to warm up, and then they hide beneath the rocks in the shade when it's time to cool down. They can't stay out in the sun indefinitely because their bodies lack a mechanism to compensate for that increasing heat. They would eventually overheat and perish in the full sun. So they always stay close to rocks so that they can get to the shade when they need to. So these lizards, of course, as temperatures have increased across the Southwest, they've just responded by doing what they've always done on hot days. They've spent more time in the shade. But that comes at a cost, because the more time you are spending hiding beneath rocks, the less time you have to be out foraging for food. So as temperatures have increased in these habitats, the calories taken in by lizards have started to go down. And in some cases where they've crossed a critical threshold, that has had real consequences. So Nervo and his team had watched several populations wink out completely before they realized that it wasn't heat killing the lizards directly. What was happening was that they weren't getting enough calories to reproduce. The females in particular couldn't build up enough energy reserves in their bodies to breed. So when it got too hot, the lizards stopped reproducing, and you don't really need a PhD in herpetology to figure out the long-term consequences of that. So another climate change theme has to do with what fans of the jungle might call the bare necessities, the simple bare necessities of life. What happens when some critical element of a species habitat just disappears? And this is really what we're talking about with that iconic polar bear image, because polar bears use that Arctic pack ice to hunt for seals. So when the ice disappears, they lose an essential hunting ground. But if we could look beyond the bears and the seals to the edge of that ice, we might see another creature that is being impacted. This creature here, a lovely little seabird called the little auk or dovekie that feeds along the edges of the pack ice where there is a rich zone of plankton, zooplankton upon which they feed. And this strategy has worked well for dovekies for thousands of years, until the Arctic ice began retreating farther and farther from Arctic islands where the dovekies breed. Places like this, like the Franz Josef Land archipelago in Russia. So dovekies have long been predicted to be an early casualty of climate change, in that the farther that pack ice gets from their breeding sites, the farther they have to fly to gather food to bring back to their chicks, and ultimately that distance will simply become too great and the populations will crash. This has long been predicted. Which brings us, though, to an important point about climate change biology, and that is that nature is not defenseless, that species are not passive bystanders to the changes going on around them. They respond, and sometimes in ways that we would never predict. So let's catch up with the story of dovekies, which comes to us from a conversation with a French scientist named David Gremillet, who participated in an expedition to a remote dovekey breeding colony in Franz Josef Land. We had indeed strong hypotheses and predictions on how they would behave, Gremillet explained, noting that birds in their previous studies had regularly flown over 60 miles to reach the edge of the pack ice. We were expecting flight times between the colony and the foraging spot of at least an hour, he went on, and then recounted what he called one of the most exciting moments of my research career. Sitting with their laptops at the dinner table, surrounded by their Russian counterparts, they opened up the first batch of tracking data and saw precisely how long the birds had been in the air. Less than 4 minutes. Instead of trekking all the way to the edge of the sea ice, the dovekies had apparently found an alternative food source right on their doorstep. But what and where? It's easy to imagine the excited conjecture and conversation that came next, perhaps fortified with a sip or two of vodka. Soon their ideas began coalescing around an entirely new hypothesis. My colleague, Jérôme Fort, remembered what we had seen while climbing the nearby mountain with our Russian friends a week before, Gremillet recalled, and described a distinct line across the mouth of the fjord, where cloudy blue meltwater from island glaciers slammed into the dark, dense currents of the Arctic Ocean. Both Fort and Grammeley had trained as oceanographers before they began studying birds, so they understood the consequences of such an abrupt transition. We both knew what this front meant, a curtain of plankton, killed by temperature and osmotic shock. For tiny crustaceans, swimming so suddenly from one kind of water into another was like driving full speed into a wall. And for anything that fed upon those crustaceans, the resulting pileup created a bonanza. Testing their theory, however, required a boat, but the only craft available was a, quote, chronically deflated dinghy, and the fuel they'd brought from Murmansk turned out to be contaminated with water. None of this was exactly ideal for exploring a polar sea, but they set off anyway and managed to sputter far enough out into the fjord for a survey. There wasn't much to see at first, but as they crossed that convergence zone between the glacial melt and the ocean water, the dovekies were suddenly all around them. The little auks were all there, Grammeley told me, aligned on the oceanic side, diving and stuffing themselves on plankton, easily picked from that underwater curtain. With that revelation, the story of dovekies and climate change switched instantly from one of decline to one of resilience. Yes, the sea ice was melting as predicted, but so were Arctic glaciers. And in places like Franz Josef Land, where glaciers are plentiful, that created an opportunity that no one saw coming. Grammeley and his team spent the remainder of their field season showing that dovekies weren't just surviving on their new food source, they were thriving. To Grammeley, the project demonstrated how one overlooked detail can have a huge effect on the outcome. Even if you think you know, he summarized, you really have to get out into the field and check what wild creatures are doing, because they very often surprise you. David Grammeley's story embodies something I heard again and again during my research for this book, how scientists went out into the field expecting to study one thing and ended up studying something else, because the conditions on the ground were so different from what they had predicted. Different in terms of the climate, but also different in terms of the lives and the activities of their study subjects. The dovekies were able to pivot quickly to a new food source because they have what scientists call plasticity. Sort of like Plastic Man, that old comic book character, right? Who could stretch himself into any shape at the drop of a hat. They're inherently flexible. And in an era of rapid change, plasticity allows a rapid response. It's already baked into the genetic makeup of a species. And for some species, it applies to a lot more than how they behave. The Humboldt squid, for example, virtually disappeared from traditional fishing grounds in Mexico's Gulf of California after a series of marine heat waves not too long ago, or so everybody thought, until surveys found that the squid were not only still present, but more abundant than ever. Instead of departing, they had responded to heat stress by adopting a radically different life strategy. They matured and reproduced in half the time. They lived half as long. They ate different foods. And under those constraints, their new adult bodies could reach only a fraction of their former size, too small to bite on the lures previously used to catch them. Their rapid downsizing had fooled everyone, even the fishers who had been throwing back the few they could hook and thinking they were juveniles or maybe another species altogether. Now, most climate change responses out in nature to date are the result of plasticity, some version of that squid or dovekey story, something that's already been baked in, if you will, to the genetic makeup of a species. But in some tantalizing cases, there are now signs of climate-driven evolution in action. And one of the best comes to us from another lizard. A lizard, a small anole, a distant cousin, if you will, of the iguanas and so on. The anole, in this case, this species lives on the Turks and Caicos Islands, out in the middle of the Caribbean. And the story comes to us from Colin Donahue, who is now at Washington University, but he had just surveyed a population of these lizards as part of a larger study looking at the impact of non-native rats on these small islands. The idea was you measure these lizards and then you measure other aspects of the flora and fauna, you get rid of those rats, and then you see how the native system rebounds once the invaders are gone. That was the idea. But then right after he finished his field season, a hurricane struck. So let's pick up the story of Colin's lizards right out of chapter 8 from the book, which also begins with a quotation, this time from another book, from The Leopard by Giuseppe Lampedusa, who wrote, "If we want things to stay as they are, things will have to change." Actually, it was 2 hurricanes, Donahue clarified, when I called to ask him how the story played out. Hurricane Irma struck first, pummeling the eastern Caribbean with torrential rains, storm surge, and Category 5 winds exceeding 175 miles per hour. Just 2 weeks later, Hurricane Maria swept through with similar force. The combined storms devastated low-lying islands, like the ones where Donahue's lizards lived, uprooting trees, flattening structures, and leaving both natural and human communities reeling. Needless to say, researchers put the rat project on an indefinite hold, but for Donahue, that setback also offered an opportunity. While his questions about lizards and rats would have to wait, he was now in the perfect position to study the effects of hurricanes. Had any lizards survived? And if so, was the surviving population measurably different from the population he'd just measured? We had no idea what to expect, he told me, but I knew we weren't going to get another chance at that kind of data. So he cobbled together some funding, headed back to the Caribbean, and found himself in a sort of scientific deja vu, repeating the exact same field project he'd just completed 6 weeks earlier. We were on a short timeline, so it was pretty much catching and measuring lizards all day long, Donahue recalled, but he described the trip with obvious pleasure, as if this were precisely how anyone would want to spend their time on a tropical island. In conversation, Donahue's enthusiasm for science borders on exuberance. He comes across as someone who probably keeps working and thinking long after other people might quit for the day and retire to the poolside bar. That may be why he recognized the potential value of returning so soon to resurvey his lizards. And it's almost certainly why it occurred to him to bring along a leaf blower. The customs officer was very confused, he said, and laughed out loud at the memory of trying to explain the science behind traveling with a large piece of landscaping equipment. We needed to know how the lizards behaved in hurricane-force wind, he told me. It was possible that they might run for it or hunker down in the tree roots. We didn't know. Since watching lizards in a real hurricane was out of the question, Donahue used the leaf blower to simulate one inside his hotel room. And I have to say, I have always wondered what the people in the next room thought about that. I mean, it's one thing if someone turns the TV on kind of loud, but a leaf blower. At any rate, Colin was kind enough to share with me a video of that experiment so that we can all see what he saw. Before I play it, let me assure you that no lizards were harmed. There is a soft net directly off camera, and all the lizards were safely caught and returned to the wild. So let's advance the screen here, and without further ado, I give you the hurricane lizard. Back legs slipping free in the wind, and now the whole lizard stretched out like a flag, flapping back and forth. More wind, until finally it can't hold on. The hurricane lizard, the wind dragging the lizard finally off of that stick. Now, in addition to getting quite a few hits on YouTube when he posted this video, it perfectly explained to Colin what he had seen in his data. Because the post-lizard population was measurably different. The surviving lizards, the ones that survived, all had large toe pads. They had large toe pads. And they also had measurably larger, stronger front legs for holding on tight. And they had short back legs, which was kind of a mystery to Colin until he did that experiment and saw how they behaved in the wind, because then he understood that short back legs reduced drag on the lizards when they were flapping like a flag in the wind, allowing them to hold on for a few seconds more, which in the middle of a hurricane can be the difference between life and death. And with this series of experiments, he realized that he had been able to measure survival of the fittest in action, natural selection playing out not over hundreds or thousands of years, but over the course of a single field season. So he realized then that he needed to know if those traits would be passed on. And he went back, measured the lizards again, saw that the young lizards had inherited those traits in the population. Then he decided, hey, he needed to know if this was truly directional selection or if it was some trait that was just sort of wobbling back and forth as the storms came and went. So he looked at the Caribbean writ large and at lizard populations throughout that geographic zone. He plotted out where all the hurricanes had been over a recent history, and he could see that wherever strong hurricanes were more frequent, the lizards had those traits. It was truly natural selection pushing those lizards in that direction, driven by changes in climate. So climate change biology then is full of just those sorts of surprises. It's full of all kinds of things that we didn't see coming. And I can tell you that we've hardly even scratched the surface in what we've talked about tonight. We haven't even talked about one of the most basic responses of all, movement, which is what species do if they can to seek out their comfort zone in this changing world. Between 25 and 85% of the species on the planet now estimated to be in motion, shifting their ranges to find those conditions that they're used to. And in doing so, upending all sorts of ecological relationships, from competition to pollination to predation to extinction. Yes, even extinction. The mouse-like bramble chemalomes, for example, in Australia recently became the first mammal species confirmed as a climate change casualty when all of its known habitat was inundated by sea level rise. So studying climate change biology doesn't make scientists worry less about the crisis, but it can help them to worry smart, allocating scarce resources to the species and systems that need our help the most. And that's important at a personal level as well, where we all struggle to allocate our limited emotional capital to this crisis. We need to know what to worry about. Yes, climate change is daunting, but I argue that it deserves our curiosity as well as our concern, because after all, it's hard to solve a problem if we aren't even interested in it. And with that, I want to turn it over to your questions so that we have plenty of time for Q&A here at the end of our presentation. Thank you for your attention.
Thank you so much, Tor. I appreciate that your presentation explains your title.
I know. You know, sometimes when I go out with a new book, you know, it's pretty hard to explain the whole thing succinctly, but I realized with this one, if I could explain the title in my presentation, that's all I really needed to do, because it's all right there, isn't it?
Yeah. So folks are welcome to put their questions in the chat or raise your hand. I see that Jean and Judy have raised their hands. Go ahead.
Yeah, hey, Thor. That was fascinating, and it certainly does make us think about what's going on out there in nature in a whole different way. Do you have any examples from trees? Because they can't migrate, and they're very slow generation times. One would think that if any group of organisms were going to be affected by climate change, it would be trees.
Jean, first of all, it's nice to see you. Hi, Judy. But that's a fabulous question. And in fact, there's a marvelous study out there that really took a lot of people by surprise. And this is from a fellow named Songlin Fei, who's at Duke, I think, someplace back east, but he and his colleagues used this massive data set from the Forest Service, looking at plots, across the eastern United States and asking the question, that very question, can trees move quickly and are they moving? And what they did was plot the center of the ranges of all these dozens of species. And they looked particularly at differences between the adult population and where trees were germinating, where the seedlings and saplings were occurring over time. Because as you can imagine, if you look at a forest and the big trees, you're looking sort of at the past, really. But if you look down and look at the seedlings and the saplings, you're looking at the future of the forest. And so by plotting this out, they were able to determine where in the ranges of those trees they were expanding in terms of where they were becoming established for the next generation and where they were declining, where there weren't many saplings and the old trees were starting to fade away. And as they did this, they accumulated this data set that showed the center point of those ranges for those species moving fast for a number of species, for many species moving measurably, but for some species moving really quickly across the landscape. And what was most striking to me about that study was comparing it to a study done with a big Audubon data set, another big meta-analysis, where they looked and saw how it was the winter ranges of birds were shifting across the landscape. They were moving too, a kilometer or 2 kilometers or more per decade. Some of the trees were moving 10 kilometers in a decade. So in fact, if you look at the data that way, it reveals that there are species of trees that can move rapidly across the landscape. Will it be fast enough for some of them? We don't yet know. But some of the research that has been done on that has been in terms of what happened after the last ice age, when these landscapes were repopulated by trees. And it had always been a bit of a mystery for some of those species in terms of seeing how quickly they came back into these barren landscapes. And now that, Songland and these others are doing this research and trying to figure out, they really can move quickly. These long distance dispersal events, some species by wind, others by creatures like blue jays and so forth, seem to be able to establish advanced populations far ahead of the edges of those species, so that they really move across a landscape a lot faster than anyone predicted. So it's really a cool area of research, and the best work on it that I've seen is right here in the States, in the Eastern US. So awesome question.
Thank you. Let's see, any other hands? Do you want to try and ask yours, Beth? Okay. Oh wait, we have 2 here. Let's see. It looks like I'm going to lower your hand, Dad. And unmute myself so you can ask your question. Go ahead.
Hi, Tor. I enjoyed in your introduction how you wrote about stories engaging parts of the brain left untouched. And it reminded me of the last time you were here at Lopez Library, speaking about Bartholomew Quill. But you also shared with us a wonderful story you had written for your son. And I wondered if you had written more stories for him, and if they were at all related to climate change, or just if you had any chance of publishing those stories.
Oh, great. Thank you for the question. Yes, I wrote a number of stories for Noah. There was a great period of time in our household where pretty much every conversation rhymed. So it was very easy to transition into writing stories for him in that vein. Of course, now I'm forbidden to rhyme in the household. It's all switched around, but I do have a number of stories that would be fun to do as books, and a couple of them that have been sold to publishers. I don't have a pub date on any of those yet, but I hope to have more of them out. But there's something that I'm really interested in right now in terms of reaching children about climate change is taking some of these science stories that we have, featured in this book, things like the hurricane lizard story, and focusing on that storytelling aspect and how can we tell these stories to a very young audience. So educating about climate change through storytelling rather than through despair. One of the, I was on a program recently with a climate advocacy, an advocate, an activist who's just spent years on this, campaigning for climate change. And she pointed out how discouraging it was for her sometimes talking to younger people because of their despair, and they're entering into their lives feeling this sense that the planet has been wrecked and that they don't feel like they have productive ways to think about this crisis. And I feel like storytelling and focusing on the curiosity aspect of addressing climate change is a really great tool for educating about this crisis. I really do feel that curiosity is more powerful and fundamentally more useful to us than the sense of despair that we feel, which doesn't tend to lead to action, but curiosity leads to learning and to action. And so I would love to find ways to translate some of these stories for a young audience so that we can start that conversation right off the bat.
Great. Thank you.
Mhm.
Amen to that.
Mhm.
I'll read those stories out loud to kids if you write
Oh,
them. for them.
good. Thank you.
Yeah, the truth of that adaptation has an element of optimism, even if it's not always a happy ending to those stories. But I think focusing on that potential positive element is useful for future generations. Let's see, any other hands or questions before we say thank you and good night? Well, I'd be a little bit curious. This is more of just a writer question. This book did come out shortly after COVID or during COVID, is that right? And what was the sort of writing process during the pandemic like for you, and how did it affect gathering your research for the book?
Sure. Yeah. I mean, certainly a lot of this book was written during the pandemic. And so some of the people that I might have otherwise talked with in person, I contacted over the phone or through Zoom or these sorts of things. A few places that I might have visited, I put on hold and did, it shifted around a little bit to, accommodate the restrictions that we were all have been living under. But, in some ways it also opened up some possibilities because certainly, people that I talked with were eager to share and to connect in a way. And that's true anyway. I've always found scientists almost invariably eager to talk about their work. But I think, with the isolation that we were all feeling, that reaching out almost, it was met with great enthusiasm. And I had some really wonderful conversations, I think, connecting with folks that were eager to we were all comparing our various COVID caves, looking over our shoulders on the Zooms. This one fellow in the Midwest had this great pike that he'd caught on the wall behind him, and we had a wonderful conversation about fishing before we ever even got to the topic at hand. So I think there were some aspects in terms of connecting with people that may have even, in some way been a little bit easier because of our eagerness to talk to one another in the midst of such isolation.
Oh, that's nice. Okay, well, I know you have another thing to get to. So Barry says thank you, and I think we can all echo that. Thank you for your time and wonderful presentation, and for your book, which is available to check out at the Lopez Library, and also I'm sure available at the Lopez Bookshop. For those folks who haven't gotten it yet, Rosie's giving you a thumbs up. So thank you so much, Tor. Have a wonderful evening.
Thanks to all of you. It's really great seeing you there in your little boxes, and really appreciate everyone turning out tonight. Take care.
Bye. Thank you. Good night,
Bye.
everybody.